In this video, we're going to be looking at electronic switching devices, devices that are used to control power in often high power situations. So there's a number of components that we're going to be looking at. They're generally called thyristors, and they're broken down into SCRs, diacs, triacs, and silicon control switches. So thyristors, as a general classification, are normally 4-layer devices. So they've got 4 layers or 3 or 4 PN junctions inside them. Have various symbols: the 4-layer diode, SCR, diac, triac, and silicon control switch. So the 4-layer devices, PN type devices with 3 junctions. The first one is the 4-layer diode, so it's just a straight diode, and instead of switching on at 0.6 or 0.7 of a volt, it can be controlled at manufacture to decide when it's actually going to switch on. The forward switch on point, it can be quite some voltage, and then once it switches on, it just acts like a normal diode and conducts in the forward direction. We see its symbol here, how it differs from a diode in that it's only got half its arrow, but it's still got its anode and its cathode in normal configuration. The silicon controlled rectifier is similar to the 4-layer diode, except it has 3 terminals. One of its terminals is called the gate, and what it does is that we can, instead of the silicon controlled or the 4-layer diode, which has a turn on point fixed at manufacture, the silicon control rectifier, we can decide when it's turned on. So we can decide at which point to turn it on. Applications for our SCR. So if we have an AC input coming in, we vary the voltage to our gate of our SCR, and we can control how much of that cycle, or when during the cycle, that this particular device, for example, the motor, turns on. The disadvantage to that is, well, that it only allows current to flow in one direction. So, for example, it would we could use it to control a DC motor from an AC supply. The other disadvantage with this particular device, the silicon control rectifier, is that you can't turn it off. It actually automatically turns off when the current through it reaches a minimum. So, for example, if we were using an AC circuit, when the current got down to crossed over the 0, the device would turn off all by itself, and we would have to turn it on at the next half cycle. One of the applications that we can use it is a circuit called a crowbar circuit, and it's called a crowbar circuit because it's like throwing a crowbar across the supply. So, for example, if we had a supply here, we had a DC power supply, and we wanted to protect it from high voltage transient on the line. If we put our SCR on here, connected it to our output like so, if the voltage here increased too much, it would turn our SCR on, and it would just immediately short out our input to our power supply. Like dropping a crowbar across the lines, it would just short it out, cause the fuse to blow. That's a crowbar circuit. The diac is similar to the SCR, or it's similar to the 4-layer diode, in fact, except it's because it's got AC after AC on its name, that means it operates in the AC range, right? So it operates in both half cycles. Once again, its switch on point would be controlled at manufacture, and it operates in both half cycles of AC. The diac is not normally used just by itself. It's normally used in conjunction with another circuit, for example, a triac, which we'll be looking at shortly, and it's used to give just a short pulse when it turns on. In this particular circuit, the voltage would build up, the diac rather would turn on, trigger the triac, and then that would also allow the capacitor to discharge. And so all we're looking for is getting a trigger pulse out of it, which is a very stable trigger pulse, exactly the same every time. The triac, on the other hand, is similar to an SCR, except it operates in AC, so it's called a triac, and we can control through its gate when it turns on, and we can control, and it'll turn on in both half cycles. Where it's used, for example here, so if we have some sort of a load, it could be anything, a motor, it could even just be a light bulb, and we want to dim the light bulb, we can delay how far through the cycle before it gets turned on, and then it turns off immediately that it goes through zero zero current through it, and then waits again until it gets the voltage signal across it to turn on. So we would have some form of circuit in here that would that trigger it, like a triac or a diac or some other circuit here to give us that delay. Triac applications. Once again, so here's the circuit again, varying the load in conjunction with some other components, resistors and capacitors, to give us a timing circuit, and a diac to give us the switch on signal. And a short pulse will turn it on, and it turns off itself as the current goes through zero, and then waits until it turns back on again. So of course this is happening at 50 times a second, and so all you'd see is a light dimming or a motor slowing down. Under normal circumstances, that would be too quick to see it pulsing. A silicon control switch is similar to an SCR, except it has two gates, an anode gate and a cathode gate. And the advantage of the silicon control switch is that we can turn it on and turn it off. So we can use it in a DC circuit, and we can turn it on and turn it off by applying a pulse to the different gates. So there's a lot of references to these circuits. We won't be investigating these circuits by themselves or building them, because especially the SCR and the diac require mains voltage, and we don't need to do that. But we will be investigating the SCR, and we see how it operates. It switches on, and then it waits until the current drops below its minimum hold on until and it'll turn off by itself, and then we've got to switch it on manually. All right, so that's switching circuits in a nutshell.